Hello, this video is on section 2.5, which is titled Reasoning in Algebra and Geometry. The learning target is to connect reasoning in algebra and geometry. A lot of the theorems I'm going to be going over. The first section is this one is algebra, and then I'm going to go over some of geometry. And of course, there will be some examples that connect all those together. So what I have written down here is a list of certain properties that can be applied in this instance specifically to algebra, and they will also be converted into geometry. So in all of these cases except reflexive, we have the beginning of our hypothesis as if A equals B, or if one number is equal to another number. So if we're looking at addition, and our hypothesis is if A equals B, then by addition we can say that A plus C is equal to B plus C. We are adding the same number C onto both sides of the equation, and this still holds true. Same thing can happen with subtraction, except instead of plus C, we are subtracting C on both sides. Multiplication is the exact same thing as addition and subtraction, except we're multiplying. So if A is equal to B, then I can say that A times C is equal to B times C. And lastly, division is the exact same way. A divided by C is equal to B divided by C. So all of these properties, the first four at least, you're taking C and you're applying addition, subtraction, multiplication, or division onto both sides of your equation, left and right. Add, subtract, divide, multiply, then divide onto both sides. Now reflexive is kind of a common sense property where all it is saying is A is equal to A. So if you have one thing and it's equal to the exact same thing on the other side, then those two things are equal. And I very rarely will use this specifically inside of a proof or theorem, but it's kind of something to keep note of, that one thing equals the exact same thing. Now symmetric is if A is equal to B, where it's left to right, A to B, then you could say that B is equal to A as long as you switch it on the same side and they are still equal. So if 2 is equal to 2, then 2 is equal to 2 as long as you're switching each side. It really doesn't matter. So they're symmetric or flipping, both sides are equal to each other. Transitive property is if A is equal to B and B is equal to C, then I can conclude that A is equal to C. This is similar to the law of syllogism that we went over in the last section, where if your hypothesis and conclusion is one thing, then your conclusion of this becomes your hypothesis of your next statement, then you could say that A is equal to C. So if you need more clarification on this, review the law of syllogism back in the previous section, and the transitive property is very similar. You will probably use this more often than you think you will. And substitution is also if A is equal to B, then you can replace your A with a B in any equation. So if you have some other equation where you C and A, you can replace it with B since you know that A is equal to B. The transitive and substitution are the trickiest ones to get, but they are the ones that you will use the most often in your proofs as we go through some more of these geometry chapters. And the last one that I could not fit on the previous page is distributive. If you have A times the quantity B plus C, you are going to multiply your A times the B, and you are also going to multiply your A times the C. So it is equal to A times B plus A times C. And based off order of operations, you have to multiply these first, multiply those first, and then you can add them together. Same thing with minus. Multiply your A times B, multiply your A times C, and you have a subtraction between them. So if you have one term on the outside of your parentheses that's being multiplied, you multiply it into every single thing inside of that parentheses. Okay, so the first example is to solve for x, and we are given that angles AOM, which is this one right here, and angle MOC, which is this one right here, are supplementary. And supplementary means that they add up to equal 180 degrees. So since we are given an algebraic expression for angle AOM and MOC, we can take 2x plus 30, 2x plus 30, add it to our x, which is angle MOC, and set it equal to 180 degrees, since they are supplementary. Combining like terms, 2x plus x is 3x plus 30 equal to 180. Subtract 30 on both sides to get 3x equal to 150. And then when you divide by 3 on both sides, you get x is equal to 50. Okay, now the directions only ask me to solve for x, which is what I've done here. But in some instances, you may have directions that say, find the angle degree of AOM. Now when you do that, you have to take your x and plug it back into this, multiply 2 times 50 and add it to 30 to get your angle measure. So be careful on what your directions are asking for and what answer you come across. Since it asks to solve for x, all I'm doing is solving for x, and then I'm good to go from there. Next example problem is again to solve for x, and we are given that the line BA is bisecting the angle RAN. So this tells us that each of the angles are equal to each other since it is bisecting. So since they are equal to each other, I set each of these equal to each other. And now from here, I can use algebra to get x by itself, subtract 2x on both sides to get a negative x equals negative 75. And I get rid of the negative, which means I get rid of the negative on both sides, so I get x equal to 75. This step right here, I solved for a negative x, but it's not asking for a negative x, it's asking for a positive one, so I get x by itself from here, and it's equal to 75. Again, you may have more steps based on the directions. In this case, we're just solving for x, so I solve for x there to get that. Okay, then we have a few more, that is the reflexive, symmetric, and transitive property. Now the reflexive property, an example is if you have two lines where one line is congruent to the exact same line. This is if either of the angles are congruent. So if angle A is congruent with angle A, then you can say that angle AB is congruent to angle AB. This is just kind of taking the algebraic theorems that were on the very first page and kind of applying them to examples with geometry. So using symmetric, we can say that line AB is congruent to line CD. Then you can say that the backwards is the same, where CD is congruent to AB. And this is if the angles between the two lines are equal the exact same way. So I'm writing them backwards. Since one thing is equal to the other, I can flip them and they're still equal. Transitive property is just like law of syllogism. So if, let's say, AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. And the same can happen to angles. If you have angle A equal to B, then angle B equal to C, then that means angle A is equal to C. But I'm running out of room, so I'm not going to write that down. Okay, so we have two examples down here, and I'm wanting you to name the property to go from one step down to the next. So the algebraic step to go from 2x plus 9 equals 19 to 2x equals 10 is to subtract. So we are using the subtraction property. Since that is the step we take, you subtract 9 on both sides. That is the property we are using to get the next step, so that is what we get. Now this one over here in green, angle O is congruent to angle W, and angle W is congruent to angle L. Therefore, angle O is congruent to angle L. This is the transitive property. Just like the law of syllogism, if these two equal, those two equal, the outsides will only equal if these two are the same, just like law of syllogism. Very last thing I want to go over is a proof. Now, a proof by definition is a convincing argument that uses deductive reasoning. You're taking some sort of theorem and proving to me that it works by using deductive reason. And the most common instance we are using this is what's called a two-column proof. And a two-column proof is where you have two things on each side of a line, and the left side is a statement, and the right side is a reason why that statement is true. So if we take a look at an example where this diagram, A, B, C, D, E, and F, and we have these angles marked as 1, 2, 3, if you are given that angle 1 is equal to angle 3 or congruent, you are asked to prove that angle AEC, this one right here, is congruent to angle DEB, which is this one right here. And a way you set it up is you have statements on the left, and your reasons on the right. So the very first statement that you are given is angle 1 is equal to angle 3. And your reason why you can say this statement is that it is a given reason. It's what we know automatically because it was in the problem. Now the next thing you could go is using the reflexive property to say that angle 2 is equal to angle 2. Of course, one thing is equal to the exact same thing if it is. Since it's in between, this is the one that we want to look at, and the reason why I can say this is, again, using the reflexive property. Since angle 1 is equal to angle 3, I can take each of those and add them to my opposite side of this equation. So my next statement could be angle 1 plus angle 2 is equal to angle 3 plus angle 2. And this is the addition property. Taking one thing and adding it to the other side, but since they're equal, I can do that without them being the exact same thing. Now my next statement that I can write is angle 1 and 2 is the same thing as AEC. Angle 1 plus angle 2 is equal to angle AEC. And that also means that angle 2 and angle 3 is the angle BED. And this is, again, I am adding, so using the addition property, I'm adding two angles together to equal 1. 1 plus 2 is angle AEC. 2 plus 3 is BED right here. And then the very last statement in order to get what they are equal to is that my angle AEC is equal to angle DEB, or congruent. Equal or congruent are the same thing. And the reason why I can say this is substitution property. Since I know that 1 plus 2 is equal to 3 plus 2, I have substituted them now as AEC and BED into my equation, setting them equal to each other, so therefore I can use the substitution property. Now I'm not asking you to memorize each of the properties, but it's nice to kind of keep them handy and written down because you will be writing down those properties and your reasons whenever you give a two-column proof.